Principal component analysis (PCA) is one of the family of techniques for taking high-dimensional data and using the dependencies between the variables to represent it in a more tractable, lower-dimensional form without losing too much information. Principal component analysis is one of the simplest and most robust ways of doing such dimensionality reduction. This article from Carnegie Mellon University shows you the math behind the PCA. As you can see, the math is quite lengthy and not easy to digest. So in this video, I will try to simplify the math and explain in a more layman terms. I will also show you how to compute the PCA manually using Python as well as using the Scikit-Learn library. Let's go to the math part first. If we have some data x and each data is represented by a vector x bar, the first thing we need to do is to center the data set. So x bar minus the mean of the whole data set. Next, we will project this centered data set to a vector w. In order to simplify the math, we assume the average of the data set is 0 and the w has a unit length of 1. So before the projection, the variance of this data set is given by the summation of x squared and sum all the x squared and divided by n. After projection to the vector w, the variance will become x bar dot product with w and taking the whole thing square and sum over all the data set and divided by n. And the variance after the projection is always smaller than the variance before the projection. But since information is more or less represented by the variance, so our goal is to maximize the variance after the projections in order to keep as much information as possible. So this is the variance after the projection. So we can compute this variance in two methods. The first is the direct method. I show a small example here. Let's say we have only two data points, x1 and x2. x1 is 1, 2 and x2 3, 4. And let's assume w is 1, 1. To get the variance, we can take the dot product of x1 and w and square it plus x2 and w and square it. And you go through the math, you will get 58. The second method to compute this variance is in the matrix form. So first we form a matrix X, which is the transpose of this X bar 1, 2 and 3, 4, and we can compute the variance by taking the matrix multiplication X and W transpose and X matrix multiplication with W. Okay, this is how it look like, and then you go through the matrix multiplication, you get the same number as the first method. So let's do in the method 2 method way. So we represent this thing by the X times W transpose and X times W, and we can bring the transpose become W transpose times X transpose and x times w, and then we can bring out the w and write in this form, and we represent this whole thing by S, and S is none other than the covariance of this matrix. Then in order to maximize the variance after the projection, subject the constraint that the length of W is 1, we can use the Lagrange multiplier technique. So the variance minus the Lagrange multiplier multiply with the constraint Wt times W minus 1, and we take the differentiation of this whole function with W, and we get this. How to get this? Here is one example. Let's assume that we want to take the derivative of this with respect to W1. We can just expand out, and we take the derivative of W1, we get 2W1. Similarly, we get 2W2, so we can simply write in this form. So to get the maximum value, we let this derivative to be 0, and we get this final expression. And this final expression is showing that W is the eigenvectors of this covariant matrix, and this Lagrange multiplier is the eigenvalues of this covariance matrix. So in order to maximize the variance after projection, we need to find out the eigenvectors and eigenvalues of the covariance matrix. Next, we will move to the Python to compute the eigenvectors and eigenvalues manually, and then also compare it to the value from the Scikit-Learn library. First, we will import the necessary libraries, and let's take this breast cancer dataset as an example. So we load this dataset from Scikit-Learn library, and we take a look at what are the information inside this dataset. We have the data, we have the target, and we have the description with the features name. So we can form a data frame using the data, and the columns is the features name, and we show this is the data frame. Next, we need to normalize the data, as one of the underlying assumption of PCA is the data is Gaussian distributed. So we use the standard scalar from Scikit-Learn to normalize the data. And this is the data after normalization. Next, we will compute the covariance using np.cov on the normalized data, and remember to take the transpose as we explained earlier in the math. Next, we will need to take the eigenvalues and eigenvectors from the covariant matrix. So we will use the linear algebra library I function from this linear algebra library from NumPy. And we can compute the contribution from each eigenvalues by dividing the individual eigenvalue respect to the sum of all the eigenvalues, and we plot out the results. That is how the eigenvalues distribution look like. So you can see that the first eigenvalue account for almost 50% of the information, and the second eigenvalue account for almost 20%, right? So next, we will use the PCA from the Scikit-Learn library. So we import the So from the Scikit-Learn library, so we import the PCA and do a fit transform on the scaled data, and then we extract the eigenvalue. The eigenvalue is represented by this explain variance ratio, and we plot out the result. We can see that the eigenvalues or the explain variance from the Scikit-Learn library is consistent with the one that we compute manually. Next, we can transform our data using the PCA, and then we can plot the first principal component versus the second principal component. We can see that the data is clearly clustered over here and here. This shows that the principal component is able to capture most of the information. This concludes the video. The code can be downloaded below. If you like to feedback on the video, we welcome your comments below. If you like the video, please share and subscribe to our channel. Thank you.